All right, so welcome to class for Tuesday, April 21st. We have a few things to go over today. So business items, we need to go through and figure out what happened with abstract submission. Hopefully you all submitted abstracts. We need to talk about posters because we need to make posters this week. Posters are, we'll talk about that. And then we'll talk briefly about, we've got the reading, the multivariate probability distribution functions. So we'll go in that order. So first things first, did each group get an abstract submitted yesterday? I got a thumbs up from Blake.
We did.
Okay, great. How about Galaxy folks?
I personally completely forgot that yesterday was the abstract submission day. So that's fun.
That is fun. Sounds like, so no abstract submitted from the Galaxy folks.
That does appear so.
Okay, so here's what we're gonna need to do. Why don't Sean, you and Bjorn, and I don't see Cindy here today, but maybe she'll pop in. We'll stick around right after everybody else is done and see if we can get that submitted. I suspect they will be forgiving about late abstracts because everything is crazy. But yeah, we'll see if we can get that sorted out.
Alrighty.
Okay, next item of business. The posters that we all made abstracts for. So we need to talk a little bit about posters. How many of you have made a poster, a scientific poster for some other purpose, either for a class or, like, for example, I happen to know Bjorn made one. Okay, so Blake.
I made one.
I'm sorry, who is that?
Dylan.
Dylan. Okay. So most of the, let's see, we've got somebody from each group then, it looks like, that has at some point made a poster before. So I won't give you I won't give you my full spiel about posters. I will add a couple of things that I normally don't. So the best way to make a poster in this environment is to make it on Google Slides. So let me actually show you how to do that. All right, let me share my screen. Okay, so if you go in here to Google Slides and you just do a new Google slide, and goodness gracious, my internet is slow. Okay, so it's going to make some new untitled presentation. The same rules apply that you've probably heard about. You know, use colors that contrast well, big fonts, all that sort of stuff. So I will strongly advise you to avoid the temptation to try to put something in the background on your poster, okay? So people, for some reason, have this desire to put some kind of artistic representation of science in the background of their poster. Just avoid that temptation. Because these posters are virtual, you can do them with either a black background or a white background. But I would recommend a white background because if you ever have to print this thing out, the person who's printing it will curse your name forever if you do a black background because the paper is white. And so if you do a white background, it doesn't use nearly as much ink as if you do some kind of black or colored background. So I suggest starting off with just a lovely blank white background for your poster. And then what you're going to want to do is come in here to File and come down to Page Setup. Oh, that's not what I wanted. Sorry. Document Details? Nope. Okay, how do I make this thing bigger?
I think it is a page setup. Either that or it's
there we go, custom.
in format.
There you go. You go into page setup and you go down to custom. Okay. This is so the standard. Well, okay. Different people do things differently, right? Different conferences do things differently. But most poster printers can print up to 3 feet wide. So the paper comes in rolls that are 3 feet long, which means that you can have that one of the dimensions of your poster is probably most conveniently 3 feet. That can be length or height, width or height, it doesn't really matter. The other thing is that most conferences or places where you're going to display a poster will have some sort of format that they give you, the space that they allocate per poster. In my experience, it's pretty standard for people to give you at least 3 feet of space. Sometimes they'll give you 4 feet, and nobody cares how tall it is. They never stack posters vertically for the obvious reason that 2 3-foot posters are very awkward to talk about at the same time on top of each other. So I'm going to make this poster 4 feet wide by 3 feet tall. You could do 3 feet wide by 4 feet tall. You could do 3 foot by 3 foot. Those are all fairly standard. But I'm going to do, I like the wider one, the wider format. And since this is virtual anyway, it doesn't really matter. But I'm going to make this 4 feet, so 48 inches by 36 inches. And I'm going to hit apply. Okay. And we're going to see it will have zoomed out. But if you go to the zoom, you'll notice that currently we're at 19% zoom, right? So if I start adding text onto this thing and start typing, what I just typed is, this is normal size text. And of course it looks insanely tiny. If we zoom into 100% though, you'll see that in fact, it actually is normal sized text, okay? Now, a couple of rules of thumb for posters. It is helpful to visually guide people through your poster, and you can do that by putting things in columns. So if you make if you make like 3 columns, right, that's easier than somebody having to read all the way across 4 feet of poster. This is why newspapers are organized in columns, because it's easier for people to read across short horizontal distances at a time. The other thing I will recommend is that your poster, so there are varying schools of thought on this, but my philosophy is that your poster should not be a standalone presentation object. Your poster should be designed so that you should be standing at it explaining what you did to the people you're presenting. Now, obviously, the virtual thing, I have no idea how that's going to work. You can record yourself explaining them. But yeah, I don't really know how that's going to work. But I would recommend building it as if you're going to be presenting it. And so what that means is you want to go light on text, heavy on pictures, okay? Find pictures that explain what you're doing. So diagrams that will show things, background images, right? By background, I don't mean in the background of your poster. I mean that explain the background of your research. So for example, if you're doing canopy waves, it would probably be good to have an image of the LiDAR data with some explanation of what people are seeing, and maybe a nice image of Kelvin Helmholtz rolls. because you're arguing that that may be what they are for background. Okay. If you're talking about the traveling salesman problem, it might be interesting to have an image of the, one of these traveling salesman routes for some, for cities in the US or something, right? And for the galaxy problem, it would probably be nice to have a nice, pretty picture of two colliding galaxies. Or maybe you could have in the abstract that we'll go over, I referenced we've had two extrasolar visitors. One was an asteroid, one was a comet, but they were from outside of our solar system. So that's another thing we could talk about, right? You could take a nice they have these, NASA made these great artist renditions of this extrasolar asteroid. So those are the kinds of things you want because they're visually appealing and because they help explain the background of your problem, right? And then you want to have something that talks about the methods you used, which are obviously all computational. But for example, you could talk about, this is where you would talk about OpenFOAM for the Canopy group, or talk about a symplectic integrator for the Galaxy group, or talk about, well, who did I miss? The traveling salesman. So you would, for the traveling salesman problem, you're going to say a lot about methods, right? And for the traveling salesman, it might be useful to throw up the differential equation you're solving. Then of course you want to show some results. All of our results are fairly preliminary. That's fine. That's not a bad thing. But show some results, show some things you've done. This is interesting. Look, it's fun, cool, whirligigs. And then you're going to have what's often called the discussion section. Conclusion is really the wrong phrasing because we're not concluding much at this point. What we are doing is discussing what these results could mean in the future, right? So this is where you'd say, for example, for the traveling salesman problem, at this point, we're just trying to find a trajectory that goes from one planet to another, right? Or a route through multiple planets. And we've started exploring, the dizzying array of possibilities. And, eventually we want to get to something that can efficiently find the best path. Okay, does that make sense?
Yes.
Yeah.
Great. All right, Blake, you've got your hand up. Is that a thumbs up or just a woohoo? All right, Blake put his hand down, so I'm going to say that was just a hands up like, yay! All right, let me stop sharing my screen. So, Sean, you have your hand up. Are you partying or commenting?
Sorry, Dr. Nelson, Chester.
Oh, goodness. My internet is having issues. Can you guys hear me? Oh, we're going to be clapping. I'll take that as a yes.
Yeah.
Yeah, I can hear you.
All right. Okay. So let's talk about, okay, so any other questions about posters? Okay, so one of the things that I'd suggest doing before we meet this week, which I know for two of the groups it's this afternoon, so you may not have time, but when you can, start generating some images, right? So generate images that you would want to go on your poster. And because that's the one thing we can't really do, we have to have something to play with. And then when we meet this week with the individual groups, we can go over sort of the posters a little bit and talk about, some specifics about what you might want to include, what you don't. Generally, it's good to include your abstract on the poster. It's not required by any means, but you may as well. So put your abstract on there. But other than that, you don't need paragraphs of text. What you really need are little bits of text to explain things, and then some nice pictures. Okay, we feeling good about posters? Iffy about posters? Great, I'll take the thumbs up. Okay, and then you'll also be able to upload a video of you guys explaining your poster. So what I'm going to suggest you do is, and those have to be uploaded by Saturday. So what I would suggest that you do is do it over Zoom. So find a time when all three of you can be there, and that way you can take turns explaining your poster. So have somebody share the screen, turn on your recording, and then while it's shared, right, the screen is shared, have somebody, take turns walking through the poster. You may want to practice this before you record it, but don't. All right, I'm back. Maybe.
All right, you're back.
Am I back?
You look like it. You sound like it.
Good. Yesterday afternoon, my internet connection decided to was basically dying every about 3 minutes, and so I could do things like write email, but video was not playing nicely. So I'm hoping we're not back to that. Okay, so
we basically couldn't hear anything you said about recording it. So
okay, I'll say that again. So on the recording side, what I recommend you do is have somebody share their screen with the poster, zoom in, right? Because the poster is big, and when it's all the way zoomed out, you're going to have issues with people seeing it. And then take turns walking through, for example, Blake does the introduction and Harmon does the methods, and Blake does the results, and Harmon does the discussion part of the poster. Does that make sense?
Yeah, that makes sense.
yeah.
Okay, you can record them on Zoom. If you create the Zoom meeting, you can record them. It'll be like this, but that's the way everybody's used to seeing the world now. So it'll work. Go ahead. Did somebody have a comment?
I think I laughed. I forgot to put.
I didn't get that. Harmon, could you say it again?
I was just laughing and I forgot to hit the mute button.
I'm glad we're all laughing at ourselves here. Okay, so the PDFs of your posters and the recordings have to be uploaded by Saturday. So once you've got a poster fairly well done, pick a time to meet and present it and record the presentation and then throw it up on the website. As far as I can tell, there's no guidance on how long those presentations should be, but I would keep them under 5 minutes. Otherwise, the file sizes start to get really big and it becomes a little bit cumbersome. Okay. Any questions about any of that? I'll say that I appreciate you guys being good sports about this whole poster thing. This is obviously not the way we want to do this, or the most effective way to do it, or even potentially an effective way to do it at all. But it's the best we got, and everybody's just trying to muddle through. So, okay. With that, let's talk about the reading. So, we're not going to have a reading assignment due on Thursday. On Thursday, we're just going to have, it'll be a fairly short class, and hopefully we'll check in on where posters are. But for next Tuesday, so who hasn't presented one of these yet?
I haven't presented.
All right, Harmon, do you want to do, so for next Tuesday, I'd like to go over chapter 5. 5.1 is just an introduction. And so 5.1 and 5.2, okay? This is talking about Monte Carlo methods.
Yeah.
So this will be fun.
Okay.
Okay, sounds good. All right. Let's see who's up today. I've forgotten who's assigned.
I believe I'm up today.
All right, Blake, take it away.
So I guess I'll start share my screen. The host has disabled attendee screen sharing.
I just turned it back on, I think.
Okay. Let's see, desktop 2. And yeah, you guys can see this? Cool. Yeah, so my section this time was 3.5, and it sort of brought what we were talking about for what we've been talking about for the past couple weeks up to 2 dimensions, and then it generalizes it to 3 dimensions. They kind of start out by talking about probability density functions for 2 variables. They have a couple conditions for it right here. Basically, like if you're at any sort of positive infinity, your probability will be 1. And if either x or y is at negative infinity, your probabilities will come out to 0. It seems like a pretty common use for coming up with these 2-dimensional probability density is for it's a tool that can help you determine whether 2 variables are independent, say x and y. Yeah, they have the condition here. I think what this just means is that f has to be a continuous function. They talk about it being monotone and increasing, but I don't know, that was kind of strange to me to hear. But I think it just means that it's continuous. I don't know, Dr. if you chime in real quick, but
yeah. So I mean, the idea.
Yeah, just like.
Let me chime in real quick on that. The point is that because it's the probability of getting some y greater than some value, right? If you increase that value, you have to have more of a chance of getting of it to be true, right? So for example, it's like saying it's the probability of rolling a greater than 3 on the dice, right? If you say, now what's the probability of rolling, less than 3 on the dice? And now say, what's the probability of rolling less than 4? Well, it has to be less than the probability of rolling, greater than the probability of rolling less than 3. Does that make sense?
I don't know, you're a little choppy on my end.
Okay, well, go ahead.
I was for anyone else. Yeah. Oh, you can find the individual projections of, like, say, for your probability density function for your single variable just by integrating out the other variable. So you'll notice that this has a dy right here. it's a function of 2 variables, spits out a function of 1 variable. And you can do this just as conversely for y. It kind of reminded me of the Maxwell speed distribution from thermal, just integrating out variables for probability distributions. Oh, and here was an interesting right here that they have is that you can have some sort of event X given some sort of piece of information. And you can compute the probability distribution of it. You'll notice that this is the function of 2 variables on top, and this integrates right here. The X integrates out, and you're left with Y. And firstly, you can change the order of this for some variable Y given some condition X. You can find a probability distribution. Here's base axis. If you just look at it from the Y-axis right here. And oh, I guess they did another PDF if X is equal to 2. And to kind of rewind a little bit, that we kind of jumped into the part talking about moments. We have our same sort of variables that we've been working with before, but there's now twice of them because there's now 2 dimensions. Let's see. Yeah, and they just kind of talk about how to find these different values. Covariances and independences, and I personally did not know what a covariance was, so I look it up, and it's the property of like some sort of form where what I think is on each projection of the probability density that that when you change the average, the center mass for the X, and multiplied by the center of the mass for the Y, this correlation test. Like, so if they're very well correlated, right, you will have the both of their points will line up and row, right? You get this graph right here, which should sort of, so if this is if this equation, these 5 graphs right here are a test of the relationship between the 2 variables, then you might think that if you get 0, that means that they're not, that they are actually linearly independent, but that is not true. And they kind of talk a little bit about that, how if these 2 conditions right here will lead you to linear dependence, and ultimately this is how they defined linear independence, I think, if I'm on the ball there. And yeah, they just kind of move into another example in here, looking at different stuff. So yeah, now they kind of move into transforming variables in 2 dimensions. They talk about moving from Cartesian to polar coordinates. They talk about Jacobian determinants and such like that, but I felt like that kind of went over my head. And yeah, they just kind of they run through an example right here of transforming a normal distribution from a Cartesian into polar coordinates. And I don't know, personally, I've done that lots of times, so I'm just going to keep, moving from Cartesian to polar, not necessarily with normal distributions, but so I'm just going to sort of glance past that. And now they kind of move into a new section about the reduction of the number of variables. They kind of just talk about making substitutions. yeah, a big piece of this was they start talking about a convolution integral, which again, it's like one of those things that I've heard about, but wasn't really sure like what it is. And and personally to me, it's a little bit hard just from looking at this form right here, which is the form for a convolution integral. But the convolution integral basically takes in two different functions, two different sort of shapes, I guess, and it tells you how they affect each other by rearranging by playing around with this convolution integral right here. And they walk through this example right here. I have to admit, it kind of confused me a little bit. And it's kind of just talking about measuring times. Like, for example, they define this triangle is equal to 2, but then they write it right here as triangle over 2. I don't know why they wouldn't just write it as 1. So, I mean, I don't know. It kind of confused me, this section. So, for example, how I was talking about how the convolution is sort of how each shape affects each other. So they have two different shapes right here, and they compute a convolution. Yeah, and they walk through another example. Let's see, I think this is still the example. And yeah, now they start moving into the determination of the transformation between two distributions. Yeah, I personally didn't really see the whole point of this section right here. Again, it kind of confused me. It kind of seemed like it was more of just an example to the previous section of transformation of variables. I mean, as you can see, they're moving from Cartesian to polar. And now they just move into like the much more generalized version of all of this. So like, what if you had more than 2 variables, you know? Like, I think for the Maxwell speed distribution, we had like 6. We had 3 momentums and 3 velocities, I think. And they come up with lots of generalizations. They give it in math talk. So my eyes personally just kind of glanced over the math talk. And then they start talking about expected values and correlation matrices. But I don't know. I had a hard time reading this as well. This looks to me like Dirac notation. And yeah, and they just kind of move into just generalizing more about how to move through the past few sections and n variables, n variables instead of simply 2. And they talk a little bit about independent and identically distributed variables. That was a pretty short piece, so there wasn't really much to say. And they talk about distributions, how distributions change when moving from Cartesian to to polar. And they talk about angles, and yeah, and they move through an example in here, and then that was just about the end of my section. So I will stop sharing now.
All right, I'm going to assume that was all brilliant because my internet was flaking out on me, and so I kept dropping in and out. But the 30-second burst that I heard sounded great. Questions? Blake, you're muted there.
I think this is like an example of like this.
You get that filth off of the screen right now, Blake. I still have nightmares from that textbook.
This is kind of like one of these in here. Well, you guys can't see my screen, but this is like a
You. Your
representation.
camera's on.
Yeah.
that like a-
So when we talk about, come on, when we talk about probability distributions, right? Multivariable probability distributions. You're exactly right, Blake. That what we're talking about is the Maxwell speed distribution, right? Or for those of you that took 301 from me, when we talk about phase space, that is a two-dimensional space that you could have a probability distribution on. So for example, if we talked about a chaotic system, figuring out exactly where it is in phase space isn't terribly useful, but it is very useful to talk about the probability distribution of where it could be in phase space, because it will not be uniform, right? The probability isn't the same that it will be 95 degrees here tomorrow as that it will be negative 20 degrees here tomorrow. Even though the weather's a chaotic system, it's not uniformly random, right? It has some structure to it. So I wanted to see if we could do an example of this, and we're going to continue our monopoly example. So Blake, I'm going to assume you talked about this concept of if you have two events that are related to each other but not the same thing, right? So they're not independent events. Talked about that?
Yes.
Wonderful. Let's talk about that in Monopoly. Let me share my screen. Okay, so here's our Monopoly thing. Let me make it bigger so you can actually read stuff. Okay. What I want to do is figure out the probability distribution, the two-dimensional probability distribution for for the rolls is going to be the number of spaces you moved on the one axis, and then the other one is the number of times you rolled doubles. Does that make sense? So for example, if you only moved 3 spaces, we know you never rolled doubles, right? Because there's no way to roll doubles and only move 3 spaces. However, if you moved 4 spaces, there's a chance, well, okay, 4 spaces, you couldn't have rolled doubles either, because the only way to move only 4 spaces is to roll a 3 and a 1 your first time, right? If you roll a 1 and a 1 your first time and then a 1 and a 1 again, you can't do it. So, but you can play these games, right? You could ask, what's the probability if I moved 5 spaces that it took me 2 rolls, right? That I rolled doubles and then a 3. What's the chances of that, right? And I could go through and ask that for everything. So what I'm going to try to do is make one of those two-dimensional histograms that Blake had on the front of that book, right? Where one axis is the number of spaces moved and the other axis is the number of times you rolled the dice, okay? So it turns out we already have all the data to do that. If you look over here, we have the, let me turn on the spotlight so it's easier to see. We already have in here this thing of the dice rolls, right? And if I run this thing, it's going to do a lot of other stuff. But the thing that I actually want is it's going to create this variable called dice rolls, which is a 6 by 100,000 array that has the sum, that has all of the rolls of the dice, right? And if you roll doubles, you roll again, and if you roll doubles, it rolls again, okay? So what I want to do here, I figured out, I used just adding up the sum of all the rolls to get the total number of spaces moved. Now what I want to do is create another piece of information off of that data, and that is how many times I rolled the dice. I could roll them once, twice, or 3 times. So to do that, I'm going to come down here and I'm going to say, okay, I want I'm going to call that number roles. And that's going to need to be an array of zeros. And it's going to need to be n turns long, right? And then what I want to do is I want to go through and count all of the time and figure out all of the times that I rolled different dice. Okay. And here's the other thing that's going to complicate this. What I actually want to do now is, instead of making a one-dimensional histogram, I want to make a two-dimensional histogram. So what I need here is an array what I need to kick out here is an array that has all of the possible outcomes, all the rolls that you could have gotten on one axis, and the number of rolls it took to get there on the other axis. Okay? Does that make sense? Yes, no, maybe? Okay. So what I'm going to do is I'm going to call this PDF 2D roll. We'll call it dubs and moves with just one M. Come on. Whoa. I don't care that a new version of Java is available. Dubs and moves. Okay, so this is going to have to be an array of zeros, and it's going to have to be, well, I need to know, first of all, I need to know what the min and max are, right? And so I can get that. I'm going to call this n moves. No, I won't call it n moves. What do I want to call it? N spaces is going to be the dice sums dot max minus dice sums dot min. Oh, I need the parentheses on the max. Okay, that's how many spaces, and dubs is simply 3, right? 1, 2, or 3. So I need to make a zeros array that is n spaces, well, by n dubs. Okay. So now all this is a big array that I'm going to use to populate where my doubles and my spaces are. And this time I'm going to do it with for loops. Okay. So here's what I want to do. I want to do for I turn in range n turns. So I'm going to go through each turn, and I need to calculate 2 pieces of information. I need to calculate how many times doubles were rolled, and I need to calculate the sum of all the rolls, right? So I'm going to make 2 variables. One is going to be called sum o rolls, and that's just the sum of dice rolls, all of the columns, or I'm sorry, all the columns on row I turn. Okay. And I'm going to have another thing called num dubs. We'll call it num o dubs to maintain the pattern there. And this one, we need to know how many times we rolled doubles. Okay. So I'm going to just start it up. I'm just going to say what it is we just started off at 0, right? We assume 0 doubles. And then we're just going to do some if statements. If dice rolls 0, I turn equals dice rolls 1, I turn, then num o dubs plus equals 1. And then we'll just layer in another one. If dice rolls 2, comma, I turn equals dice rolls 3, comma, I turn.
Couldn't they both be equal to 0?
Ah, but they can't on the first one, right? Because the first one, the first roll, we don't allow zeros.
But aren't you checking the second one now?
Yes, but it's inside the if of the first.
Oh,
So
yeah.
I only check the second one if the first one already came back as doubles.
Got it.
Right? That's a good catch, though. Okay. And then we're just going to add another one. Num o dubs plus equals 1. And we'll do one more. And I'm just going to copy and paste because it'll save me a little bit of time. I'll have to tab that over. And finally, if I had doubles the second time, I can check one more doubles with 4 and 5, right? And I add one more to it. Okay, now I've done all this. So now for each turn, as I go through this loop, I'm going to calculate the total number of spaces moved, which is sum o rolls, and the number of doubles I rolled, num o dubs, right? And I just want to record those. So I'm going to hold off on this PDF business for a minute. And for now, let's just, I'm going to call this turn results. And what this is going to have in it is just the total move and the total number of spaces moved and the number of doubles for each time you rolled. Oh, by the way, I've done this wrong. There are actually 4 possible number of doubles. You could have 0, 1, 2, or 3, right? Okay, so the turn results is going to be an array that has, it's 2 things we're recording by n turns number of things, okay? And all I want to do in this for loop is just save those 2 things. So in turn results, sub I turn 0, I'm going to put the sum o rolls, and in turn results 1, I'm going to put the num o dubs. Okay, so now if I run this thing, in addition to everything else it's going to do, and I go to my variable explorer, oh, what didn't it like? Okay, well, we're not even there yet, so I'm just going to comment that out. We'll run this thing. Okay, so it did a bunch of stuff, but now I have this this thing down here called turn results. It's 2 by 1,000. The first space is how many spaces you moved, and the second one is how many sets of doubles you rolled, right? So for example, On the first time, you rolled a 3, you had no doubles. The second time, you moved 13 spaces and you had one set of doubles. Okay? The second time, you moved 15 spaces and had one set of doubles. Let's see if I can find one. Okay, this one, number 4, right? You moved 9 spaces, but you had one set of doubles. Now, you could also have moved 9 spaces without rolling any doubles, right? You could have rolled a 6 and a 3 or a 4 and a 5. But somehow we moved 9 spaces, but we rolled doubles. So for example, maybe we rolled snake eyes and then the next turn we rolled a 7. Okay. And you can go through and see these different possibilities. Okay. Okay, now the question is, what do we do with it? And for one-dimensional histograms, there are some very nice ways to deal with that. But for two-dimensional histograms, there aren't quite as nice of ways. So we're actually going to build it ourselves. Before I do that, let me figure out what happened to that n spaces that it threw a fit about. Oh, it made it a float. Fine. I can fix that. We just do int. And now when I rerun the thing, it'll make my number of spaces a float. Or an integer, which is what I want. Okay, so now I'm actually going to make my histogram. And I'm going to actually call it hist instead of PDF because the PDF is the normalized version, right? So now I've got this array, which I called hist 2D dubs moves, which I'm going to actually just call it hist 2D because I don't want to type all that every time. And what I'm going to do now is I'm going to go through all of my turns again. And turns. And I'm just going to put things in the right bin, right? So I'm going to say that hist 2D sub. Okay, now I have to be a little careful here because the index isn't, I can't just put int turn results sub 0, I turn. Why not? What's wrong with this, what I'm trying to do here? Oh, there's one other piece. I haven't done the second piece, which is turn results 1, I turn. Okay, what am I trying to do here?
Well, you're trying to go through, just like index through all of your turn results and just every location where that you want to populate, you're just adding 1 onto that histogram.
Right. So each time I go through, I find the right bin, the right number of moves, and the right number of doubles, and I just add 1 in that bin, right? I'm building a histogram. Okay, why isn't it going to work? Well, let me run the thing and it won't work. Ah, see, it didn't work. Let me make this bigger if I can. Is that big enough? Can you read that?
Yeah.
All right, so it doesn't like that. It's yelling about integers or slices. Let's see, what doesn't it like? Turn results. Oh, turn results are an array of floats. So I need to make this an integer. But I'm going to guess it still won't like it. And let's try that. Ah, there we go. That was the error I was expecting. Okay, it yelled at me that index 34 is out of bounds. So I gave it the total number of possible spaces you could move, there are 33 possibilities, right? And we can see that here because the minimum is you move 3 spaces, and one more than the maximum is 37 spaces. We can see that on our plot, right? The maximum you ever move is 36 spaces, which you can't even see because we'd have to zoom in. But there you go. The most you can ever move is actually 35 spaces. And the least you can ever move is 3. So because there's possibilities on either end of that, right? You've got 33 potential moves you could make, right? So why don't we ever see that? Or why is it yelling at us that 34 is out of bounds?
Because in your for loop that you need I turns in range, n turns +1.
I actually don't, because I only have n turns, right? I only have 100,000 turns. But you're on the right track. It has something to do with indexes, right?
Well, basically, like your hist2d plot has like a bunch of values for like the number of spaces, like turn results axis from 0, 1, and 2, which are never getting populated because the smallest number of spaces that there are is 3, and then that offset is like going up to the upper end too, and it's trying to populate like 35, 36, and 37, but those don't exist on the histogram either.
Right. So here's what I'm going to have to do. I'm going to have to subtract off of this because this is generating numbers from 3 to 36, right? But my array only indexes from 0 to 33. So I just have to subtract 3 off of it. Or another way you could think of this is I need to subtract off minus, and I'm going to just save it. I'm going to call it min spaces. I'm just going to save as the integer of dice sums dot min. And I'm just going to subtract off here min spaces. And now when I roll a 3, right, when I move 3 spaces, it puts that into index 0 in our array. So I just have to remember now that the index in my array isn't the number of spaces I moved. It's the number of spaces I moved minus 3. Okay, so now if I rerun this whole thing, we should see something happen. Oh, it's still yelling at me. Why is it still yelling at me? N spaces is, oh, I'm not accounting for the 36. So let's actually do this. I'm just gonna, instead of actually looking at this, so the problem here is that in my 100,000 rolls, I never rolled triple sixes, right? I never rolled 12, 12, 12. So I can fix that by simply saying that I know that the maximum is 36 and the minimum is 3, right? And then I'll just say down here, the minimum is 3. Okay. All right, let's try that one more time. Nope. Oh, I know. Okay, sorry. I'm getting myself confused. Because 36 is a possibility, I actually need 37. I'm sorry. I need 34 possible bins, right? Because I need one for 3 and one for 36. I need to include the endpoints. All right, one more time. There we go. It ran. Okay. Now we have this thing. Now what do we do with it? Right? We have this 2-dimensional histogram. Well, let's come down here to the bottom and let's plot the thing. So I'm going to do plt.figure, and we're going to do PDF of moves and number of doubles. Okay. And I'm going to do a P color plot because I like P color. And so we're going to plot up. Well, we need X and Y axes, right? So for my X axes, I'm going to put roll bins up to, but not including the end, right? For my Y axis, I'm just going to do a range up to 4. Wait, I want 3, so up to 4. And then I'm going to give it my histogram, my hist 2D. And I could give it more than that, but let's run it and see if it actually works. Nope, it yelled at me. Why are you yelling at me? Oh, I need to switch the order. All right, try that. Okay, we made a thing. Okay. Now, it doesn't look like much of a thing, but it is a thing. Okay. So you can see here, well, first of all, it would be helpful if I put a color bar on this thing. That'll help us know what we're actually looking at. So there is the most likely thing to have happen is to roll a 7, right, with no doubles. That's the highest probability of anything that's going to happen, right? And you can see that the probability is going to fall off as you go until you get out here, and you can't really see it very well, right? But it's there. So now we have a 2D probability distribution, right? We have the ability to ask ourselves, what are the chances of any one of these events happening? Or we could ask ourselves, what are the probability, what's the probability distribution of spaces you move, assuming you roll at least one set of doubles? Okay? We can start playing these games. Does that make sense? What I'm talking about here?
Yeah.
So, so it's actually probably just as useful to actually look at the array. So if we look at hist2d, right? Now it's flipped, and it's probably small for you guys. Let's see if I can zoom in on this. No, it won't let me zoom. Well, you can kind of see here, right? That it's showing us where it is impossible, right? It's impossible to move 24 spaces without rolling doubles. In fact, it's impossible to move 24 spaces without rolling doubles twice. And you can see over here, it's impossible to roll doubles 3 times and have an even number. I could have told you that beforehand, right? But what's interesting is that there's only the chances of rolling, the most likely number of spaces to move if you roll doubles 3 times is 22 spaces, 19 plus 3, right? That's the highest probability move you can get if you roll 3 doubles, okay? And you can start playing these games, right? You can start looking at taking these things apart and figuring out, now, what are my cuts, right? So for example, if the question is, I moved 14 spaces, what are the chances I go to jail? Because in Monopoly, if you roll doubles 3 times, you go to jail, right? So 14 spaces, 961 of those were off 1 set of doubles. 58 of them were off of 2 sets of doubles, and 36 of them were off of 3 sets of doubles, which means it's very unlikely that that will happen, but not 0. And you can start actually getting at these things. Okay. Does this make sense a little bit when we talk about two-dimensional distributions? Okay, I know we're over time, but there's one more piece I want to show you, and it'll get to this covariance idea, okay? What I want to do now is I want to do just a new figure, and I'm going to do a scatter plot of, on the one axis, I'm going to put all of the distance moved, right? So this is my turn results, sub 0, and all of them. And on my y-axis, I'm going to plot the number of doubles rolled, all of them, okay? And when I run this thing, it's going to pop up my window here, and we're going to see something interesting, okay? So now, this isn't the most informative plot because the dots are right on top of each other, but you can automatically see something here. These are not randomly distributed variables. They're not independent of each other, right? There is a definite trend here. If you moved a lot of spaces, that implies that you probably had a higher chance of rolling doubles multiple times, right? If you moved a lower number of spaces, you had a chance of rolling doubles a lesser number of times. This is the idea behind covariance. These are not independent quantities. They're related, right? In this case, they're both derived from the same basic set of data. And so they are covariant. They have a positive covariance, right? Meaning that the further you moved, the more likely it was you rolled doubles to do it. Does that make sense?
Yeah.
So covariance is important because if you ignored that and you just asked what are the independent probabilities, right, of total number of spaces moved or total number of doubles rolled, you would be missing out on the fact that there's a relationship here, right? There's a variability that relates the two. Now, this is the kind of stuff that drives experimental physicists nuts, because when you have errors that are sources of error that are covariant, you have a problem, right? So for example, let's suppose I want to measure, I have some measurement technique for measuring the polarization angle of light, right? But my technique is covariant, right? So that measurement is also covariant with the temperature in the room, right? Meaning I'm more likely to get a big angle when the room is hot, and I'm less likely to get a big angle when the room is cold. Now I have a problem because now I better keep track of both of those things. Otherwise, I'm going to get faulty results, right? I'm going to get results that are influenced by something else. And often something that I don't actually care about, right? You're not doing that optics measurement to figure out the temperature in the room. And so you can get these kinds of covariances. They drive experimentalists nuts, but they're important to keep track of. Okay, I've talked for too long, and my internet has been terrible, so I apologize for all that. Questions, comments, concerns?
So can you go back to the 2D histogram real quick?
Yes.
So, it looks like the histogram is only showing like 3 values of like double, of like the number of doubles, but shouldn't there be like 4 columns on that histogram?
Yes. That's an artifact of the way P-color plots things. We could probably do a better job if we didn't use P-color. So P-Color, it makes boxes by using the corners of the points, right? And it colors the box, so it generates colors. We could probably plot this better some other way. I'll have to think about that. Okay, I'll come back to that on Tuesday or on Thursday. Okay, I'll come up with a better way of displaying the 2D histogram. Sound good? Okay, well, I will leave it at that. I'm meeting with the Canopy group at 2 and the Salestronaut group at 3. Is that correct?
Yep.
Did you still want to talk to Galaxy Group about getting our thing submitted? Because
Yes. So I'm going to stop the recording. I'm going to stop sharing my screen, and I'm going to